Hey guys, today we are starting the formulas that are on the back of your formula chart. So we're going to start with the double angle properties or the double argument properties. And you're going to ask yourself, how do I use double angle properties to simplify expressions and solve equations? So those are the applications of those properties. We're first going to start with where do these things come from? So let's start. Okay, so the first thing we're going to look at is why is sine of 2x equal to that formula on the back of your chart. So, looking at sine of 2x, we can always rewrite that as sine of x plus x, because that's x plus x is 2x. Then if I use those sum and difference formulas that we talked about, last week, we would know that this expression on this side would have been sine x cosine x plus cosine x sine x. Again, that's just the sum and difference properties that we did in the past, where your a would be x and your b would also be x. Now, if you notice here, both of these expressions have a sine and a cosine in them. They are technically like terms because if you have multiplication, you can write them in any order. So I could write this sine x cosine x plus sine x cosine x, which would get me 2 sine x cosine x. And if you notice, that is what is on your formula chart. And so that is why that works. Okay, now let's look at cosine 2x, because that one looks a little bit different on your formula chart. So I'm going to break it down the same way. Cosine 2x is equal to cosine x plus x, because there's two x's in there. So if I use my sum and difference formulas with x being a and x being b, we'd have cosine x, and then since this was a plus sign, it would be subtraction, using my formula chart, minus sine x sine x. Well, we know that we can rewrite that if there's two of one thing as cosine squared x minus sine squared x. And that's the first formula on your formula chart. So that's the first one that they show you that cosine 2x equals 2. Now you have to be careful here. This guy is not equal to 1. Okay, cosine squared x minus sine squared x is not 1. If you remember that Pythagorean identity, it looks like this, or cosine is first. So if we add them together, we'd get 1, but not if we subtract them. So this is a completely different identity. Now, looking at these, though, we want to figure out where did those other formulas come from that they have on the double argument for that second one down. So if you look at the second one, it says 1 minus 2 sine squared x. And so what I want to do here is make this in terms of all sines. So if I rewrote this in order to get cosine, something new for cosine, I could subtract sine from both sides, and I would know that cosine squared x equals 1 minus sine squared x. So if I replace this entire cosine squared x term with 1 minus sine x squared, and then I subtract sine x squared from it, if you see there, we have like terms again, and so that gets you 1 minus 2 sine x squared, or sine squared x, sorry. And so that's that second formula on your formula chart. Same deal for the third one. It's just now you're going to rearrange this in terms of cosine. So I want to make sure I get rid of any sines that I have in here. So I would have sine squared x is equal to 1 minus cosine if I subtract cosine from both sides on that first one. Okay, so again, I'm going to leave my cosine squared x alone. Then I'm going to replace the sine squared x with 1 minus cosine squared x. Be careful here because you'd have to distribute this negative in here. So you would get that there would be cosine squared x minus 1 plus cosine squared x. And so that is where that 2 cosine squared x minus 1 comes from. Okay, so again, any of these are legitimate to use for cosine of a double angle. You can use any of these things, so that can come in handy when you're trying to prove things. And then finally, we're not going to go through this guy for tangent. There is a formula for tangent, but remember, we can always rewrite tangent as sine over cosine. So if you're solving a problem and you've already found sine and cosine, and then they ask you to find tangent, why would you plug into this crazy formula if you already have two answers that you know? Okay, and so that is where all of these formulas come from. Again, this is at the top of the back side of your formula chart. And again, you will have your formula chart on this test too. So let's do some applications of these double angles. The first thing that we're going to see looks kind of familiar. They give you a ratio for sine as 3/4. That's not one we have on our unit circle. They're giving you a domain restriction and then they're asking you to find the sine of 2x, the cosine of 2x, and the tangent of 2x. First thing I know about this is if I am looking at a picture, I would have that my angle would be in pi over 2 to pi, so this would be in quadrant 2. So when I draw my angle x in, I'm going to draw it in quadrant 2. Now I'm going to label the sides with what I know. I know that the opposite over the hypotenuse is this. Then if I do my Pythagorean theorem, I would figure out that this would be the square root of 7, 16 minus 9, square root. Now the only problem is where it's located is you now have to make that negative because of the quadrant that it's in. So at this point you have your triangle drawn, and we're going to use those formulas in order to find these pieces of information. So the sine of 2x, if you use that formula chart, you would know that the sine of 2x is 2 times the sine of x cosine x. Well, the sine of x cosine x are just ratios that I can pull off of my triangle using SOHCAHTOA. So I'd have 2 times the sine of x would be opposite over hypotenuse, or what they gave you. And then the cosine of x would be adjacent over the hypotenuse. And now this is just a fraction-y thing that I can simplify. So if I time straight across, remember this is over 1, I would have 2 6 times negative square root 6, I would have this would be negative across the top. 2 times 3 is 6 times the square root of 7, all over 4 times 4 is 16. I can simplify this down a little bit and get negative 3 root 7 all over 8. And that would be your answer for sine of 2x. Okay, so again, if you can draw a picture, life's pretty easy. Okay, now if I want to find cosine 2x, I have lots of options here. I can use any of the ones that they give me, and if you wanted to just use sine, since that was what the ratio they gave you, that's cool. I'm going to go ahead and use that first one, cosine squared x minus sine squared x. So be careful on this type of problem. We are going to have the cosine squared, which I already found was negative root 7 over 4, and I'm going to square this entire fraction. Same deal with sine, that was 3 over 4. And so when I square this, the squared kind of does distribute into the parentheses, so you would square that top, which would give you positive just 7, all over 4 squared is 16, minus 3 squared is 9 over 16. Now I can simplify this down because it has a common denominator, thankfully. 7 minus 9 is negative 2 over 16, which simplifies to be negative 1 over 8. Okay, finally, the tangent of 2x, and I have run out of some space here. The good thing about the tangent of 2x is, again, you can use that crazy formula. However, you already know what your values for sine of 2x and what your value of cosine of 2x. Work smarter, not harder. So if I go ahead in here and I take the value I found for sine, so negative 3 root 7 over 8, and I want to divide it by the value I found for cosine, negative 1 over 8. If I remember my fraction rules, I'll keep the first thing, change the sign to a multiplication, and then flip over the second one. And so what this is going to do, my 8's will cancel, my negatives will actually cancel, and I'll just find that the tangent would be root 3, or 3 root 7. Okay, and so again, smarter, not harder. The last application we have for this are going to be those general solutions. So they're going to give you an equation, and they're going to ask you what's the general solution and what are the values of that angle on a certain domain. So for this one, it would be 0 to 2 pi. So when I'm looking at this guy, this looks something like what I've seen. I know sine of 2x equals 2 sine x cosine x. So if I go ahead and divide this side by 2 and this side by 2, that would get me what I wanted. Now, this is an equation. It is okay to do stuff to both sides. Now, when I'm proving something, I have to pick a side and stick to it. But this is just solving an equation. So I'm okay to do stuff to both sides of that equation. So this would leave me with 2 sine x cosine x equals 2, 1. And now, at this point, I know that 2 sine x cosine x is actually just the sine of that double argument, or sine of 2x. Okay, this is stuff we've done before. So now at this point, I have to get this guy to be the inverse sine, because remember, the only way to get that sine to the other side to get x by itself is to take the inverse sine of both sides. So I would know I have the inverse sine of 1 equals to 2x. And two things I can do here. You can use your OIO chart. And then we know this is SOHCAHTOA, and you have your 0, your 90, your 180, your 270. Or you can put that in terms of pi, or you can do what the y value is. So you're looking for the y value to be 1. If I look in my OIO chart, I see that the only place where sine is 1 is at 90 degrees, or pi over 2. So I'm going to write this in radians because I have x's up here, and the second part asks me in radians. So the only place on my unit circle where sine is 1 is at pi over 2. Remember, this is a general solution, so I need to add all of those coterminal angles, so 2 pi in, and that's going to equal to 2x. Now I've got to get x by itself over here, divide everything by 2 or times by 1/2. Hardest part to remember on this one is to remember to give that 1/2 to everything in the parentheses. So my general solution would be pi over 2 times 2 is 4, and then that 2 is going to cancel, plus pi in. Okay, remember, usually we have 1 or 2 general solutions. This one just happened to only have 1 because it was on one of those borders. Okay, so that was part A. Part B asks me to find all the values on this range from 0 to 2 pi. So if I look at my general solution, I already have a positive value. I have pi over 4. Okay, if I went ahead and I said to add pi to this guy, if I had pi over 4 plus pi, which is the same thing as 4 pi over 4, that would get me 5 pi over 4. And that is still in that range. Okay, if I went ahead and I added another pi over 4 to that, I would get 9 pi over 4. And that is outside of my range of 0 to 2 pi. Same deal if I subtracted pi over, or pi from both sides. Not both sides, just subtracted in general. That would get me negative 3 pi over 4, and that's not in the range they wanted. So these are the only 2 solutions in that range. Okay, and that's basically what we do with double angles. You can prove things using double angles, but remember, you have your formula chart there all the time. Have a great evening.